Okay. So yeah, last week we covered setting up the project. So bringing in your schematic, your PCB, your libraries, setting all the rules and all your preferences. I know not many people were around for that one, but just general setup stuff. So this week we're going to go on with starting off the schematic, how to set it up, how to place it, good techniques and spacings and all that kind of stuff. So to start with, or we're going to be making just a simple buck converter around just this 12-to-5 adjustable buck converter. It's a standard one, and I've done little lessons on it before, but we're gonna go through and just make a simple circuit for that chip. So starting off, since we know what our design is going to be, it's just going to be what would be a good way to do this? Never mind. What we're going to do is it's just going to have an input header for power in. We're going to have our actual buck converter, and then we're just going to have our input header for power out. We're not going to go into any more detail at that for this. So starting off, we want to look at the datasheet for the buck converter that we're using. We already have this. We already have our libraries made. So in the Phantom library, we already actually have this buck converter made up already. So we don't have to worry about making that up. So you see what the typical circuit can look like, and I think there's another, yes. What the typical circuit looks like. We have the SO8 package. So this is kind of what we would base ours on. And we know we want a 12 to 5 volts. And since this is adjustable, it has the ability to be as the feedback resistors tell us if we want our voltage to be 1 to 5 volts. We have to change the resistance values for our ones that we go to the feedback pin. And we saw how the feedback pins in the previous buck converter and the LDO lessons. But we know we want our 5-volt output. So we're going to need 124 kilo ohm and a for the range of voltages are C1, or C7, 5 to 22 picofarads. Our inductor, we want to be at 3.3 micro, and then C8 and 9 be somewhere 22 to 68 micro. I think that was all. Yeah, those are the only considerations we need to look at for this design, or the modifications that we have to make sure we take into consideration. So with that, we can start with our circuit. That one. So there's a couple ways we can go about starting the circuit. First off, we're going to place part. So place part or PP, and then we're going to change our library to power because that's where the buck is, and we can just drag that in. Now the couple ways that we can make our circuit is by first dragging in all the components that we know we need and then later organize, or start going component by component, wiring it up properly, and go by that way. I generally like just dragging in a lot of parts for a given section, and since this schematic is just an easy components built around one buck converter, I would just drag in everything related to that. But the other thing we can start with is the connectors. We know we're going to want, could have done that better. We're going to have an input header and we're going to have an output header. So our input, if we do PG, or PO, that creates the power ports. So our input and output are both going to have a ground connection. And if we hit tab, we can change the net name to 12 volts and switch the style around to a bar. Rotate. And we'll set it to 5 volts. And PW for place wire. And we can just wire up the two headers. So this is a good start for what we can do, is just make our input header, make our output header, so we know that we're dealing with 12 to 5 volts. It's best if you are to label them 12 volts, 5 volts. You could also go 5VO for 5.0 volts. That's one way of going about and it's a very typical way to write it, just so it's obvious to say that it's meant to be 5 volts flat. We could also just call it V out, and if we wire everything up with this V out notation, it will all work fine. It'll anything about, but it becomes a little confusing. You're not too sure at a quick glance what we're supposed to be outputting. So typically, your power nets, you want to be writing the actual voltage level. So we got the headers out of the way. And for headers especially, there's no, we don't care about making sure that 12 is on pin 1 and ground is on pin 2 at this point. to us, it makes no difference. Maybe when we get to the PCB stage, we'll see that maybe there is a better orientation by having 12 volts on the bottom, but typically not a concern, and definitely not at this point. One thing to notice, and I think I made a note of this in one of the previous lessons, when you're laying out everything, it's common practice to go power to ground being top to bottom, and input to output being left to right. So we can see that our power points are all pointing up and our grounds are pointing down. So power is going from top to bottom. And our inputs are coming from left and our output is on the right. That's just, that's kind of general practice, and it's, and it'll be on similar to how we do it on, for the actual full schematic itself. Power, you'll typically see in the top set. So power will have it pointing up, our grounds will point down. The enable pin is going to be inputs into the buck, and then the BST and the SW are the actual outputs of the converter. So we can see that it all kind of follows into out, left, right, power to ground, top to bottom. There's nothing wrong with having a ground going straight out or even technically pointing up. It just looks wrong. So we try to keep to the convention of grounds down, power up. Now the next, or any questions on anything at this point before I start bringing in a bunch? Cool. So just referencing this real quick, we know that R1, R2, C7, C8, 9, and L1, those were all the components that had a variance on them depending on our output voltage. So we know these values may be different from what the example shows, but other than that, we can basically pull in the rest of these values as we see them. So we're going to have our enable, we'll have a 10 key pull up. We have a couple 10s, 10 micros on our input for bypass, 1 micro, 8.2 nano we can change for a more reasonable or an easier value that we actually have in our library. And then we'll just carry on. But yeah, so for a simple design like this, I would just go dragging in everything. So we can start with capacitors. And based on our designs, since we know this board is only going to have the buck converter, it can be a fairly small board where we know we're not restricted on space or anything. So we don't have to go extreme and get 0402 components, because those are just very small, and they're very hard to deal with, especially if you don't have to. So 0603 should be the minimum. 0805 isn't even a bad one, since we know we have a lot of space to work with. And then the second thing to check out is the voltage range. Since we're dealing with voltages up to 12 volts, we know that all of what we see here is basically fine. You can see there's this one. We do actually use a 22. Having a 10-volt rating, so we know that we can't place this one on any of the input pins, since its rating is lower than our 12-volt input. So always going to want to make sure when you're placing capacitors that the voltage rating is at least higher. Typically, you want to go at least double for to improve the life cycle of the component. I need a couple 22s that are going to go on the output, so let's find that they're only 10 volts. I need a 0.1 micro. And this is kind of just how I do it. Knowing based on kind of this layout, I know where components kind of need to be layout, like what pins they need to go to, and that kind of stuff. So I will loosely lay them out in that kind of position, so I know that's connecting, and I know that this is on the output. We need a what was that? We're just going to sub in a 10 nano for that 8.2 nano. For what it is, it's close enough. Is my 10 micro. The capacitors we need in our design, and then we'll head off to resistors, and then again, same thing. We don't want over O2s just for the sake of dealing with them. And then we typically don't have voltage limits, but rather power limits, which for the most part, for most designs, we don't have a concern about. Most of these are rated 1/8 watt to 1/4 watt, and in most application that's fine. There's nothing. We're not doing heavy current draw through these resistors. They're more for pull up, pull downs, and the voltage divider for the feedback pin. So it's not too critical that these are heavily power spec'd. 124K. That was all the resistors we needed. And then the last component we need is the inductor, which was a 3.3. So now we have all of the components that we're going to use thrown into the circuit. And we can start laying them out a little bit more properly now. So again, this is just how I typically go about it when I'm dealing with a small section of a circuit. I'll throw in the main IC or the main, whatever the major component is, and then all of the complementary passive components around it, just to kind of speed up or to have everything there and lay it out all at once. But there's nothing wrong with first bringing in just this one part, doing the wiring, and starting off the wiring, bring in the second part. It just creates more back and forth and can be slower if you do it that way, depending on the design. To start with, we'll look at our two input capacitors, our bypass caps. We saw that these are just on the input, running in before we hit the device. What we can do is I'll bring the power net. Change this back to power ground. One thing I found is if you are going back and forth between naming your power ports like this, you can mess up your design if you add an extra space in your naming. So this ground with the space will be different than the ground with your proper ground that you had before. I think that's what actually messed up one of my earlier BMS designs. Or if you have this all lowercase compared to an all uppercase, they won't actually match. So when you're naming these power ports and all nets for that case, you want to make sure you have consistent naming and that you don't mess that up. Anyways, back to our bypass. We go and wire these up. So we can do this, also shift, if you're holding down shift and hit space, that cycles through the different wire styles. So angled, whatever line squared off. In circuits, in the schematics, you always want 90 degrees. You want just straight. You just want straight corners. You don't ever want to see we don't want any of this in our schematic. It's just design guideline. But So for our bypass caps, we can do this and then just have this floating off to the side. And then just have 12 volt come straight into the VN. There's nothing wrong with this, since it is, when you're looking at the actual connection of it, your VN, if you were to just, the VN node is just going straight to 12 volts. So there's nothing wrong with having the VN just go to 12 volts and then have your bypass caps having that 12 volt and ground connection off to the side. So you're not trying to cluster up your schematic all down here. So when you have designs that have a lot of bypass caps, it can be especially helpful. But even at this stage, we can have our bypass just give them the power ground connection they need and then throw them off to the side so they're not going to clutter up our design. So we'll go with that. So all we have is our 12 volts coming in. We can throw it down our ground connections. We saw that the enable just requires a pull up. Volt. So we can see that we can have multiple power nets. It's all the same 12 volt, it's fine. But we could just as easily have this single 12 volt. Let's get rid of that. So what we could do is just have this single 12 volts and have it connect to all of the items. It creates the same connection. We just do this. This is purely just a matter of how you want to lay out your schematic. I find it cleaner when you break it off, so you have multiple power nets. That way you don't have wires coming across the full thing and potentially overlapping on each other. But it's whatever you want to do, because electrically, connection-wise, it's the same thing if you do these 3 different power ports, or if you were just to have the one and wire off to each, to all of them. There's no difference in that. Then the SS pin gets a pull down. The VREG 5 pin has a bypass. Then we have our feedback pin that with the 124 and the 22.1. We saw a cap bypassing this. So here at this point, we want to avoid any 4-point nodes or T intersections, or not T intersections, cross intersections. just because it can be confusing sometimes, especially in designs that have more more stuff going on, more crossovers and components and everything. It may be difficult to decipher whether this capacitor is supposed to also connect as feedback, or is it just supposed to go capacitor resistor and this feedback goes through. Sometimes it can be unclear. Just are all four things actually supposed to be connected, or are they supposed to overlap? So the better way to line it up is with these T intersections. So only ever having three lines going into a node, just so you can clearly see that, okay, yeah, this is definitely supposed to connect to this line. Same with this, just so there's no confusion in crossover points. And then connect it up on the other side. Another thing to point out is we have a large schematic. Don't be afraid to use it all up. There's no need to bring in components to have a nice tight look to it, because you have the space and might as well use it. And you always want to at least space it out so your components are readable. So we have the space, we'll space it out as far as we need. If you are running into times where you're having to bring it in close, and it might get a little clustered where your designator is overlapping, you can actually rotate the designators themselves, and you'll sometimes actually see this by having your designator and comment running up with the component. But that's only when you have to, because your designs are super compact. Should you be doing all of this stuff so that they can be in close? It's not bad if you want to do this typically. Just have that as it is right now. But as long as you're spacing components out, so everything's readable and it's nice and clear that connections are being made to the correct components. Questions on anything I've gone through? No? So we'll finish up the basic layout. And then same thing here, making sure that you're not too close that these start to get clustered. Just spacing everything out so we have so that's all the components actually wired up. And I left all of these ground connections blank for the time being, just to show the couple of ways that we can do this. Again, we can do the same thing we did with how we had our multiple power ports for the input. We can have a ground pin going to everything that needed its own ground pin. So this is just a clean way of having everything together, or having everything separated so that you don't have wires running across the full length. But there's nothing wrong with bringing everything to a central point. So that all of your components are just sharing a single ground port. And the connection, electrically, the connection is identical between this and the previous, where we have a ground point on each. It's purely just preference and how you want to make it look. I do prefer having them all independent for the most part. Maybe if I have a couple capacitors that are sitting close together, I would tie them to one, but it is purely just how you want to make it lay out. And same thing, having them all on this, bringing everything down to a single straight line of grounds, that's purely just me on how I like to lay it out. But there's nothing stopping you from having everything close up and right on the pins. These kind of things are just aesthetic. It's about your schematic. And then we need to finish this up. Ports back. So in our case, following, they have two VO pins, just because the feedback pin has to wrap around, and because I could have made this schematic symbol a little nicer. So we didn't have to have two, but again, same thing. If we if we wanted to, we could bring this all the way around. So this, again, same connection. They're both tied to 5 volts to the output, like they should be, but you just have to run a wire all the way across, which, in my opinion, doesn't look good. So just having your 5 volt to 5 volt on either side works out fine. And now everything is electrically connected properly. So that is the basic of the schematic layout. So it's everything, this is technically everything you need to have your schematic ready to go. You have a header that will take your input, 12 volts and ground. The 12 volts goes through the bypass caps into the device. It's got its enable pin that's pulled high. It does all of its buck converter work, and then it outputs a 5 volts, and that 5 volts goes to the output header. Now, in most of our designs, it's fine to have our input ground and our output ground be the same thing. We're all just dealing with low voltage. It's fine for the most part. But one thing, especially for the high voltage boards, and any of the boards that deal with the attractive system, our input may be 168 volts, and the high voltage ground, where our output is only going to be 5 volts, and we want it to interact with the low voltage side. In this case, we could change our signal to signal ground, and actually name it V ground, or ground for isolated ground. It's also not too important that you change power to signal. As long as you change the name, that's what will disconnect it. So when we're dealing with high voltage systems, or systems that we want that isolation between high voltage and low voltage, or just the grounds in general, for whatever purpose it may be, you want to make sure you change one of your, or both of your, ground names. So we would call low voltage ground, these bypass interact with the high voltage, and then we could go down the line of splitting off what's interacting with the low voltage and what's interacting with high voltage, and have them be properly isolated as needed. 12 to 5 volts, everything's okay, sharing a common ground. Any questions on the layout? No, nothing? Raphael, Alina?
I'm good.
Looks good. Cool. Then the final thing we want to do before moving to the PCB is giving everything a net name. So this is so that we can have meaningful wire names when we shift it over to the PCB. What I mean by that is if we go place net label, so PN, we got our net, and we basically connect it to all of the blank pins. So we simply just call this one feedback big. Now, what this does is make it so these connections have, just basically gives them a name for when we shift over to the PCB. Otherwise, when we try to connect things on the PCB, we'll get things like, it'll just say C1, pin 1 connects to U1 pin 4. So it'll have some net C11, U4, 1, which is just a mess to look at. But by putting this net name, this net label on our wire, when we go over and we look at that component, it'll say SS in this case. So, like, we don't have to do it on the VIN because the power ports act as net labels as well. So this VIN will show up as 12 volts. Same thing with this side of the inductor. This branch of wires is just connected to 5 volts. Same with ground. Those act as net names. So now we have all the components we need. They're all tied to the proper voltages. We have net labels on everything. So now we want to go to Tools, Annotation. We can annotate schematics quietly. It'll just automatically do the annotation for us. So there's 15 requiring update. Go ahead. So it automatically went through, and instead of these being all R question mark, C question mark, like we had them, it will automatically give them names. C3, R2, R3, R4, blah, blah, blah. All the way around, everything's labeled. Everything's ready to go. If you want a little more control on that, we can go to Tools, Annotation, Annotate Schematics, and you get this pop-up. This is useful when you have multi-page schematics and maybe you just want to annotate the one schematic that you just finished, but you don't want to bother with the others that still need a little bit of work or maybe more components added. So you would only click the one that you want. If you care on how they're ordered, you could change across and down, all of that kind of stuff. Really doesn't matter. And then you just update change list. It's saying we're going all of these to become all of these, so I'll accept. And it gives you the operation. It's modifying all of these. So we validate, execute, and we can see that they all passed by and went through. So we can close, close. And same thing. It did all the labeling for us. So that is everything you need to know. Yeah, so then when you're basically finished with the schematic, one good thing to do is go through and compile. For us, this brought up, it'll bring up 2 new folders, nets and components, which basically just brings in all of your nets, all these net labels that we did, plus the power ports, and then the different classes of components. So capacitors, headers, inductors. Really doesn't matter, we never actually look at those. But if you have errors in your schematic, when you go to compile, it'll pop up with an error list if something's wrong. Something wrong just being it's not compliant to a rule, or maybe you only have if you only have one ground pin, or you only have one pin that doesn't connect to anything, that'll come up as a warning saying, hey, you have this pin that's just floating. Sometimes that can be ignored. You know what you're doing and you didn't want to connect it. Or it can be a good reminder, be like, oh, I forgot that. So when you finish off the schematic, it's good to go through, right-click on your PCB project and compile. And now your schematic is finished up and ready to move on. The other thing, if we care about our title block, if we do properties in the general tab where we set everything to metric and all of our size. If we go over to parameters, we can actually start modifying. And we can actually update this full list to give it a title, name, revision, all of that kind of stuff. For the most part, it doesn't matter, but it can be nice, especially if you probably do the number of sheets in a design. So actually properly counting off that this is page 1 of 1, what the actual title saying it's a buck converter, or this is the T-cell revision 1. It's good. It's just good for documentation's sake, but not super required or necessary for most of these low system designs that we're doing. But it is good to have this updated on real projects. But that is everything about schematics, I think. Any questions before we call it a day?
Yeah, I got a quick question for you, Jared.
Yep.
For like when you connected all the grounds together and then you split them off, and you said that you liked one way better or the other, for like Team Phantom, are we gonna have like a designated like standard for all the drawings to show up a certain way, or is it just going to be whatever we kind of feel comfortable with?
It's going to be whatever you feel, because this really doesn't affect much, and it doesn't change the style too much, especially on this the smaller scale things. We're not going to hold anybody to this standard. It's just however you want to go about it.
All right, thanks.
Any other final question? Oh, actually, one thing that I've noticed is actually a decent practice, and some of our members actually do it, is placing text strings everywhere for labeling sake. So boost the text way up, just to kind of label. I think this is more useful on larger projects, where you basically give the full page a title, and one of the things you could be doing is connectors, and you can go place drawing tools line, and you can have things boxed off. We're good at drawing boxes. Just to kind of break up kind of components. I'll show you a good use case, or where we implemented this well. So Gabe did this really well for the VCU. So labeling at the top of the page saying this is connectors. This is the connector for the dashboard and the pedals. This is the high voltage connectors, the power in, your breakout connections. This is for power current sensing. So your LEDs, your the monitoring, the multiplexer. So just having kind of a overall title to your page, and then breaking off, saying what each little section is. So this is the LDO, these are the decoupling, this is the pins. Because when you have, if you were to do something like this, where it's, you got a lot of things going on, it can be hard to actually tell what's going on. Like, I'm not sure what this section is actually meant to be doing, so it's, but you can see there's, so you'd have to actually look in and be like, okay, there's watchdog, okay, USB related things, there's your JTAG connector, okay, so this is related to, USB related things and the power on and the programming side of it. Whereas if you do something like this and you just straight up say CAN transceiver, you don't have to do much digging. You can tell right away that, okay, I'm looking at the CAN transceiver. And so this is a good good practice all around. In our case, for this little board, I mean, we don't really need to label off connectors because that's a little obvious. But having the buck converter header on the page is quite useful. Just for a simple sake of being able to quickly look at the sheet and know exactly what's supposed to be going on. And the other thing is notes. So if your design has variation to it, or you just want to put general notes around, so layout note, place decoupling caps as close as possible to the IC pin. So you know that your decoupling cap, you want to be as close, although you may not be able to show it in the schematic because of everything that's going around it. The component may be way off to the side, but you just want to make that note clear that you should be placing this cap as close as possible. And then same thing, especially if you have 0 ohm resistors or jumper resistors, is what they're also known as, which just slightly modify a design. So, connect this if needed, don't connect it if otherwise. Yeah, so in case an RC filter is needed, it's there. But so anytime you have something that you might want to modify in the design, put a note to it. Or just in general. Yeah, so again, you don't show the microcontroller in this one, but you want to make it known that these caps should be placed as close as possible to them. Another good one, I don't know if Gabe did it, having kind of a list of what your pins are supposed to be doing or what their pins are supposed to be connected to. Or something like I threw up in the BMS. When you have a bunch of different voltages or a bunch of voltage like port pin, power ports on your board. So I have a VREF, a VM, VDAG, VP, VIO. just labeling what the voltages are supposed to be. This is a very good debugging tool. So once the PCB is made and we're going through the debugging of it, we can see, we can go find the VREF pin and we can poke it and we can compare to what we're supposed to be seeing based off of this little guide and make sure that it is the true voltage that we're getting on the output. So notes are really good when you have designs that need minor modifications, or if they have a lot of different power pins, having a voltage guide is really good. But you don't need it for everything. When to populate or not populate is helpful. In our case, we could say, place decoupling caps as close as possible to the IC, but I wouldn't worry about it in this simple of a schematic. Okay, now I'm done. Yeah, so nothing more from any of you? Cool.